Okay, just for like to be totally like neutral and everything. I thought she was gonna just talk about like the census and the elections closing today. So anyway, okay, the census is important, and yeah. So I do want to like emphasize what she's saying about that. That it is really important, both just as a statistical thing to have an accurate count of people, but also as a financial thing. The state gets money. And I guess in lots of ways from federal sources. It also determines, if you follow the Constitution, the original reason for the census was to determine how many representatives there are from each state. Okay, so, oops. Cool, sure. Okay, so today is sort of a loose ends day. On Tuesday, I did chapter 19, kind of start to finish. And today I wanted to kind of go back and do things that happened while I was gone a little bit farther. So last week, Professor Purvis did chapters 20, 21, and 23 sort of light. He did sort of the beginning of each chapter. And essentially did the math from each chapter. And that's the way that the order that, or the way that he actually teaches it is to do that and then come back and do them a little bit more completely. And I thought that would actually work well in terms of having someone lecture for me, to have me come back and sort of finish up all those chapters anyway. So that's the way we're doing it. So I'll do sort of the end of chapter 21, and chapter 23 today. And I think I'm actually going to get pretty close to being done with that. See how it goes, but which means that I'll be a little bit ahead of the syllabus. The syllabus has me finishing chapter 23 on Tuesday. So so I'm not sure if I'll exactly finish chapter 23 today, but I'll get pretty close. So we'll get into chapter 26 certainly by the end of Tuesday. We're skipping chapter 22, we're skipping chapter 24, we're skipping chapter 25. Okay, questions about anything? Okay, so end of chapter 20. So if you remember from last time, talking about chapter 19, I defined what's called a simple random sample. So simple random sample is just like draws. It's draws made without replacement. It's a probability method. If you remember from last time, probability method is any sampling method that involves chance. So simple random sample is just like drawing tickets from a box. Without replacement. So everything we've done with box models up to this point has assumed that the draws are made with replacement. So you think about rolling a die over and over again, the die is the same every time. It doesn't change. Same thing with tossing the coin. All these examples that we've done so far assume that the drawing tickets is done with replacement. Chapter 19 is the first time where we kind of talk about having the draws done without replacement. Okay? So simple random sample is this idea from chapter 19, and this is commonly the way that actual samples, public opinion polls are done in real life. They're not going to call the same person twice, right? If they want to do a survey, they want to think of it as a sample that's done without replacement, so that they're not calling back the same person, right? They can't draw that person's ticket more than once. Which I think makes some intuitive sense, right? If you want to do if you want to find out the opinions of a bunch of people, it's sort of a waste if you call back the same person. You're not getting a new opinion. So that's the sense in which intuitively the public opinion polls are like draws without replacement. Okay, so the math turns out to be a little bit different. Okay, so let's think about which one is more accurate. So when I say more accurate, I'm thinking in the background about this idea. Actually, either one of two ideas. Either you can think about this as this kind of probability model, that the observed value is somewhere around the expected value plus chance error. You can think about it in this context. Or if you want, you can think about it in the context of chapter 19. The statistic is somewhere around the parameter. Could be off because of chance error or bias. So as I said before, the bias is the subject of chapter 19, and we'll sort of restrict it to that chapter. I won't discuss bias a whole lot outside of that chapter, except to hope or assume that it's close to zero, generally. Okay. Alrighty, so when I say, would it be more accurate to do our draws with or without replacement? When I say more accurate, I'm sort of thinking, well, you know, what do I think about the chance error? What do I think about the chance error if I do my draws with replacement or without replacement? So any thoughts? Which do you think is going to give me, in general, a smaller chance error or a small standard error? Any thoughts on that? Or which one intuitively you might prefer to do? Yeah. Without replacement would be more accurate? You want to say why? You don't have to. Don't think it matters? So let's say that I want to know what percentage of the people in this class are, let's say I want to know what percentage of the people in this class can flare their nostrils. Flare their nostrils. Like, I don't know if you can see me. Maybe the front row can see me. Okay, so, you know, you make your nostrils go in and out. Sort of. Oh, that's a bad example. So if you can't see me. Let's say I want to know what percentage of the people in the class are registered Democrats, say, okay? So suppose first of all that I can only ask 10 of you, okay? So if I ask 10 of you and I do it with replacement, if I do it with replacement, it's possible that I might ask the same person twice, right? So you might think that I'm getting a little bit less information that way. If I do it without replacement, I'm guaranteed to get 10 different people. Suppose there are, I don't know, 150 people in class today. Suppose I can ask 150 people. What's going to happen if I do it without replacement? It means that I ask everyone, right? So if I do that, I actually know the answer, right? If I do a sample of 150 people out of 150 people without replacement, I actually get it exactly right. If I do it with replacement, I might be off by a little bit, right? So in that sort of extreme case, you might think, okay, well then it's got to be better to do it without replacement. And it turns out that to a smaller extent, it's true even if I ask just 10 people, that I don't really want to risk asking the same person twice because I don't get as much information that way, okay? So in terms of the accuracy, I should tend to have a smaller chance error, just kind of intuitively, I should tend to have a smaller chance error if I do it without replacement as opposed to with replacement. The expected value is the same regardless of how I do it. So like say the percentage of Democrats in the class is, I don't know, 75%. So I should expect, if I just ask a bunch of people, I should expect to get about 75% as my observed value, right? It might be a little bit higher, it might be a little bit lower, but in general, that's the way you should think about it, okay? All right, so suppose I don't know. Suppose I don't know what the percentage of Democrats is. I do, statistic. I do it sort of thinking about it this way. I take a sample of, I don't know, 10, let's say 20 people. 20 people, and I don't know what the parameter is, but whatever that statistic is, there's no particular reason, if we ignore bias, there's no particular reason if I take a simple random sample of 20 people out of the class, or if I take a sample with replacement, there's no reason why my statistics should be kind of systematically higher or lower than the parameter. So again, you sort of think that the statistics should be about whatever the parameter is but maybe off because of chance error. And as long as no one lies and everyone responds and I do it as a simple random sample, there's no bias. There's just no systematic error. Okay? So just to kind of summarize, if I do either a simple random sample, which is without replacement, or if I do a sample with replacement, expected value is going to be the same, and the chance error will tend to be smaller if I do it without replacement. So there's actually a formula for figuring out what that should be. So standard error without replacement turns out to be pretty close to the standard error with replacement, but it's multiplied by what's called a correction factor. And I'll often abbreviate the correction factor CF. Okay? That CF is this formula. So it's the square root of population size minus the sample size divided by the population size minus 1. Okay, so let's think about special cases for the correction factor. Just a couple things I want to say. So first one is suppose the sample size is equal to the population size. So what happens to the correction factor? It's 0, right? If the sample size is the population size, if those are the same, then the correction factor is 0. And this is the example I was talking about. If I have 150 people here and I ask everyone, I ask everyone in the whole class, correction factor is 0, standard error without replacement is 0, meaning that there's no chance error. I've actually asked everyone, so there's nothing random going on. Okay? Okay, so that's one special case. Another special case is if the sample size is 1, what happens in this formula? What happens here when sample size is 1? Sample size is 1? 1, right? So sample size is 1. I get population size minus 1, population size minus 1. Divide, I get 1. Whole thing is 1. So why does that make sense? Why should the correction factor be 1 when the sample size is 1? Kind of look at how we're using it. Yeah. Yeah, if I'm taking one person, if I'm only going to ask one person, it doesn't matter if I replace that person or not, because I'm not going to ask anyone else, right? Okay, so in those two extreme cases, asking one person or asking everybody, you sort of see how it works, how the correction factor works. You're multiplying by it, so yeah, if your sample size is 1, it's not going to change the standard error. This is the usual calculation we're doing. The usual calculation we're doing, all the boxes we've dealt with so far are done assuming the draws are with replacement. So then if you take that regular calculation, multiply by the correction factor, you get this kind of more refined or more accurate calculation for what would happen if we do the draws without replacement. So anything in between, right? Typically, you're going to ask something between one person and everybody. Anytime you ask anybody anything in between, or number of people that's in between, this is going to be between 0 and 1. Okay? So in this case, correction factor equals 0. In this case, correction factor equals 1. In general, it's somewhere in between. Okay? So if I ask like half the population, then I get population size minus half the population is a half. Sort of half the population on top, roughly the whole population on the bottom, so the whole thing would be square root of a half. Okay, so just roughly, if I sort of ignore the -1, that's about right. If I ask about half the people, the whole thing comes out to be about square root of a half, which is about 0.7. Okay, so it's making the standard error somewhat smaller. And again, another way to think about that is that if the standard error is smaller, I expect the chance error to be smaller. It means that things are more accurate. Okay, so this correction factor can be used with any standard error, meaning this could be SE sum, SE percent, SE average. So correction factor. whenever draws are without replacement. For any standard error. So I mean sums, percents, and averages. Okay. It doesn't really matter that much, and part of the reason we haven't talked about it until now, it doesn't really matter that much if the population size is much bigger than the sample size. So for example, if in the field poll example I did last time, the population was all California likely voters. So there are presumably millions of them, right? There are a lot. And the sample size was like 748. So we have like millions minus 748 divided by millions minus 1. Well, that's really, really close to 1, right? Millions minus 748, millions minus 1. When you divide those, you're going to get something so close to 1. When you take the square root, it makes it even closer to 1. That you don't really care. There's no point in really calculating it because it'll be like 0.99999 or something like that. So when you multiply by the correction factor in that case, it won't really matter. So we'll typically ignore it. All right. So when do you know? What I'll tell you is that. So I want you to use it whenever sample size is at least 10% of the population size. Okay? So if the sample size is less than 10% of the population size, you can use it. It's technically more correct, but it usually won't matter much. It's only when the sample size is a pretty big chunk of the population where it starts mattering. So intuitively, what's going on there is that if the sample size is very small compared to the population size, like if I only, maybe the 150 people in here, if I only ask 10, that's 10% of 150 would be 15, so 10 would be less than 10%. If I used it there, if I asked 10 people at random from this class and I did it with replacement, it's pretty unlikely that I would randomly ask the same person more than once anyway, right? So intuitively, it doesn't really matter that much whether or not I do it with or without replacement if the sample size is a very small fraction of the population, because the chance of asking the same person more than once is small anyway. If you think about the field poll example, even more true. If your population is all likely voters, millions of people, and you're only going to ask 748, even if you did it with replacement, there's relatively small chance that you would randomly call up the same person on the phone twice. Okay? So for that reason, the sample without replacement is almost the same as sampling with replacement. So you can kind of ignore it. Mathematically, if you do it, if you actually calculated it, you can see that it's close to 1. It's not going to change your answer much. Okay, any questions on this? Yeah. What if sample size is bigger than population size? Then it can't be draws without replacement, right? It has to be draws with replacement if your sample size is actually bigger than the population. Well, the correction factor is only relevant when the draws are without replacement, right? So you're not going to use the correction factor. You just calculate the standard error the way we've been doing it. Like if you have 100 die rolls, the box just has 1, 2, 3, 4, 5, 6. The population is just 1, 2, 3, 4, 5, 6, right? And you just calculate the standard error in the usual way. Does that make sense? Yeah. Okay. Any other questions? Okay. Yeah, so just to emphasize that idea, everything we've done so far, all the calculations we've done so far, assume that the draws are with replacement. Okay? Chapter 19, I talked about last time, the idea that in reality, a lot of these public opinion polls and stuff are technically done without replacement. And this is the first time I've addressed that mathematically, okay, that difference. And again, the reason why we kind of sweep this under the rug sometimes and why we haven't talked about it before now is that in many, many cases, the population size is way bigger than the sample size, like the field poll, stuff like that. It's only when the population size is kind of maybe relatively small, like this class, that you might actually sample more than 10% of the people in the population. Okay, other questions? Okay, so I'll do one quick example of this, and I'm going to do it, it's just a sort of artificial math example. Suppose I have 400 tickets in a box. And it looks like this. So I have 100 tickets marked 1 and 300 tickets marked 0. And I take 100 draws without replacement. Okay. And I'd like to find the expected value and the SE for the sum of the draws. So there's a little bit of a tendency, I think, to think that this SE, this correction factor is for percents because it's in chapter 20 where you do percents. But in fact, like I said, it can be used whenever the draw is without replacement, any kind of SE. So it could be sums, percents, averages, whatever. Okay, so find expected value and SE for the sum of the draws. As I said, the expected value is going to behave the same whether or not I do it with or without replacement. And I hope that makes intuitive sense. Like, if I take 100 draws out of here, whether I do it with or without replacement, I expect a fourth of the draws to be ones, right? Out of the whole box, a fourth of the tickets are ones. So if I take 100 draws without replacement, I expect about 25 ones. Doesn't matter if I make those draws with or without replacement. Okay? To do the math, you get average of the box. Add them all up, we get 100 out of the 400, so that's 1/4. And EV sum is number of draws 100 times average of the box. So that's, like I said, that's 25, which I think makes intuitive sense. Okay, so now to find the standard error, the SD of the box, square root of 1 minus 0. I'm using this shortcut back from chapter 17. So it's the big number in the box minus the small number times square root of 100 over 400, 300 over 400. And that comes out to be about 0.433. And now the SE for the sum is equal to the square root of the number of draws times 0.433, which is 4.33. Okay? So this calculation so far up to this point is done as if the draws are with replacement. Okay? So this is our usual calculation that you're used to. This is treating it as though it's with replacement. So since it's without replacement, I need to multiply by the correction factor. So without replacement, I'm going to take 4.33, and I'm going to multiply by the correction factor. The correction factor is square root of population size is 400 tickets in the box, minus 100 sample size, divided by population size minus 1. Okay? And that is about 3.75. Okay, so you can see, it doesn't make a huge difference. It's changed the standard error for the sum of draws. It's changed it from 4.33 to 3.75. Makes it a little bit smaller. That reflects that it's a little bit more accurate. You might think of it that way. It's a little bit more accurate to do the draws without replacement. Again, you can see if we did 400 draws, we'd put a 400 here. The standard error would be 0, which is reflecting that if I took 400 tickets out of that box, I got them all. I must have gotten, if I took 400 draws, I must get 100 ones. No chance error. OK? So questions about this? Oh, yeah, so I guess maybe it's clear, but this is more than 10% of the population, right? 100 draws out of 400 tickets. I'm drawing 25% of the tickets. So it is more than 10%. So it should be making some difference. Like I say, it doesn't make a huge difference, but it's sort of right to do this calculation. OK, questions? OK, so I've done this in this kind of strict box model context. This correction makes sense and works anytime you're calculating a standard error. So if you're doing like a confidence interval, as discussed in chapters 21 and 23, anything else you're doing, anytime you're calculating a standard error, it makes sense to use this as long as your draws are without replacement. I want you to do it for sure if the number of draws, if the sample size is at least 10% of the population size. OK, I don't care if you use it if the sample size is less than 10% of the population size, as long as it really is draws without replacement. OK. Anything anyone wants to ask or say? OK. So that's that end part of chapter 20. So now what I want to do is do basically the end of chapter 21. So I think Roger Purvis, in my absence, talked a little bit about confidence intervals. Yeah? A little bit? Confidence intervals? Sound familiar? Yeah, OK. So I want to talk more about them and do some examples and stuff, but I'm going to assume that you've sort of seen the basic idea. Well, maybe to just remind you, I'll just say just a little bit. The confidence interval is used, you can say this in a few different ways. Sort of the way I like to think about it is that a confidence interval is used to give a likely range for the parameter. So this is in the context of this idea that the statistic is somewhere around the parameter, might be off because of chance error, might be off because of bias. So the idea is that we've taken a sample. We don't know what the parameter is, but we're estimating it based on the statistic. And we'd sort of like to know not only what's the estimate, but get some idea of how accurate that estimate is. So kind of the first step is to attach an SE, attach a standard error to our estimate. And this sort of gives us a give or take number. The next slightly more, I don't know, refined or advanced way of thinking about this situation is to think about what's called a confidence interval. So for example, 95% confidence interval, I'll abbreviate confidence interval, CI. 95% confidence interval is found by taking the statistic plus or minus 2 SEs. Okay? And the 95% and the 2 SEs are related. We know from the normal curve that 95% of the area is within 2 SDs. And in the context of random stuff, chance error, things like that, 95% was within 2 SEs. Okay? So if I asked you for a different confidence interval, like if I asked you for a 68% confidence interval, it would be the statistic plus or minus 1 SE, because 68% goes with 1 SE. Okay? So you can do whatever confidence interval you want. This is pretty common, is to do 95%, 2 SEs. But it's not like a law that says every confidence interval has to be that. You can sort of do whatever you want. OK, so I'll say a pretty good amount about what this means in more detail. But I do want to do an example before I get to it. So I'm going to use the field poll data. And so there's 748 likely voters. 43% of them, I'll say, support Boxer. Okay, so what they were actually asked is basically, if the election for U.S. Senate were held today, would you vote for Boxer? And 43% yes. The context of this is comparing this to Tom Campbell. So they were said, you know, if Boxer is the Democratic nominee, Tom Campbell's the Republican nominee, would you vote for Boxer or Campbell? 43% said Boxer, 44% said Campbell. And as I did before, I'm just going to treat them as ones and zeros, with the ones being Boxer supporters and the zeros being everyone else. So as I said last time, this is maybe a little bit unfair to Boxer, because presumably some of those undecided people might support her. And as you can see, 43 versus 44, it's basically even right now. Okay? All right, and this was this survey was done March 9th through 15th, so it's fairly recent. I guess almost a month old now. Okay, so what's going on here? We have a box. Who's in the box? California likely voters. We've taken a sample of 748 of them, and we know how those people feel. We know that of the 748, 43% support Boxer. What's in the box? Well, there are a bunch of ones and zeros. We don't know what percentage of all California likely voters support Boxer. Okay, that's sort of what we're interested in. That's the parameter. That's what we're trying to estimate. So typical book notation for this situation is to draw question marks in front of those. We don't know how many of each, but we do have some idea, right? We have some idea that about 43% of the people in the box support Boxer. That's our statistic. It's our estimate for the parameter. Right? The parameter is this number. It's the percentage of all California likely voters who support Boxer. Okay, so I'd like to get a confidence interval for that, meaning a likely range, a range of points that is likely to contain the parameter. So I'm going to go from the statistic plus or minus 2 standard errors, and there's this little bit here that I don't know the SD of the box, right? So in this calculation here, and in all the calculations I've done so far before today, Roger Purvis, I think, did this when he was here, but everything so far, I can find the SD of the box. I know what's in the box, and I can calculate the SD of the box directly. Here, I can't. I don't know the percentage of ones in the box, so I can't find the average of the box. I can't find the SD of the box. However, I do know that the percentage of ones in the box is somewhere around 43%. So you can do this thing called the bootstrap method, which is to estimate the SD of the box based on the SD of the sample. And it turns out that this is quite accurate in practice. That even if the 43% is not that exact, the estimate of the SD will be pretty close. And you might have noticed this when you've calculated SDs before. If the box is 50% ones, 50% zeros, like a coin toss, SD of that box is 0.5. If you have something close to 50% of ones in the box, you may have noticed that the SD is pretty close to 0.5 anyway. It doesn't make much difference. This could be off by a fair amount, and you still get a pretty accurate idea of what the SD is. So in fact, for this case, the SD of the sample is oh, I'm sorry, I didn't write it down. I just wrote down the end calculation. 1 minus 0. I'm sorry. If anyone has a calculator, you might actually find this. I just found the SE. I didn't do the intermediate step of finding the SD in my notes. Okay, so square root of 0.43 times 0.57. If anyone feels like doing that, you can just yell it out. Or 495. Okay. So you can see it's pretty close to 0.5. If this were 0.5, it would be 0.5. And even if you're all the way down at 0.43, it's pretty darn close to 0.5. So my point is just that even if the true SD of the box were pretty far off, like 0.4, 0.5, this estimate of the SD is going to be pretty accurate. It's going to be pretty close. Okay? All right. So that, like I said, that's the SD of the sample. We're going to pretend like that's the SD of the box, or estimate the SD of the box using that. So then when I go to calculate the SE, SE sum is equal to square root of 748 times 0.495. That's about 13.54. And SE percent. So this is a formula done in my absence. This formula is SE sum divided by the number of draws times 100%. So SE sum is 13.54 divided by number of draws is 748 times 100%. Comes out to be about 1.81%. So 95% confidence interval is 43% plus or minus 2 times 1.81%. Okay? And for purposes of doing the calculation, I've left a few significant digits here. In reality, this is already fairly rounded, probably. It's probably not exactly 43. Out of 748 people, they probably rounded this number off when they reported it. So in a way, it's a little bit silly to have 2 significant digits here in my standard error, which is even estimated, when my actual estimate itself doesn't have any such significant digits. Okay? So I'm writing this for purposes of calculation, but really might at least take off the hundredths digit and leave it like that. Let me tell you what the field poll says about the results. If you go to the field poll website and kind of like read through about 5 pages of text discussion of this survey, at the end they give you some information and some math. And I just want to tell you what they say and how it kind of relates to our discussion. I'll just read the first part. They say, so actually maybe I'll say something about random digit dialing before I say this, which is that they say that their overall sample is weighted to align it to proper statewide proportions by party registration, region, and other demographic characteristics of the registered voter population. So essentially what they're doing here is they're doing this random digit dialing thing I talked about before, is this dividing up into different strata by region, by party registration, different things, and taking simple random samples within those groups, essentially. So trying to make sure that the sample that they end up with is representative of the population of the state. Now, this is different from doing a quota sample. The reason why it's different from a quota sample is that they're doing this randomly. They're doing their selection within each little group randomly. When I talked about quota sampling, which is not a probability method, the interviewer is making some personal decisions, like going out, like I said, sort of going out to Sproul and asking people, okay? And because of that, there's some discretion left to the interviewer. It's not actually random. It might feel kind of random, like whoever you talk to is sort of random, but it's not random in the sense that each person is equally likely to be chosen the way that it is if you do a simple random sample. Okay. So that's what they say about that kind of chapter 19 sampling issues. They also say sampling error estimates sampling error estimates applicable to the results of any probability-based survey depend on sample size as well as the percentage distribution being examined. So that's just a fancy way of saying that, you know, it depends on how many people they ask, the 748. And they say the maximum sampling error estimates for results based on likely voters in the general election is plus or minus 3.7 percentage points at the 95% confidence level. So the field poll says, what they say is plus or minus 3.7% at 95% confidence level. Okay? That's another way of saying that 95% confidence interval is 43% plus or minus 3.7%. Okay. So our calculation is slightly different, right? What we're doing is 43% plus or minus 2 times 1.8, which would be 3.6. So what you'll see a lot of times in this is or 4.3% plus or minus 3.6. Okay. So what you'll see a lot of times if you look at results based on public opinion polls and stuff like this, what they're doing is slightly more conservative than the bootstrap method. What they're doing is they're actually, rather than doing bootstrap a lot of times, what they do is they assume that the SD is 0.5, okay, which is more conservative. That's actually, I don't want to get into the details of the math, but that's the biggest that that's the biggest the SD could possibly be. If you have ones and zeros in a box, if you have a really lopsided box, the SD ends up getting smaller and smaller. If you have half of each, the SD is a half. So often what you'll see in public opinion polls or in results from things like that is that they assume that. They kind of assume the worst for the SD. Rather than doing bootstrap estimate, they'll do something a little bit more conservative, which is just to say, well, worst that could possibly be is if the real box had 50% ones and 50% zeros, calculate the SE based on that. So you'll see sometimes that if you do the calculations we're doing them, you'll get something a little bit smaller than what you might find in their explanations. So that's why it's a little bit different. Okay, but they're essentially doing the same thing intuitively, right? Any questions on that? Yeah. If the data doesn't follow the normal curve, can you still do that? Does the data follow the normal curve? What is the data? Data is a list of numbers, right? For this example, what's the data? Yeah, you get a bunch of zeros and ones, right? You have 748 numbers, 43% of them are ones, the rest of them are zeros. Does that follow the normal curve? No. If I drew a histogram for that, it would just have 2 bars. It would have a bar for zeros, it would have a bar for ones. It doesn't look like the normal curve. Okay? It doesn't matter. It doesn't matter because what we're curious about is whether the probability histogram for the statistic follows the normal curve for this thing. So if you think about like chapter 18, we did normal approximation for a lot of things like coin tosses. The coin tosses themselves don't follow the normal curve. You just get a bunch of zeros and ones. But when you're taking like the sum of a bunch of draws from a box, like number of heads and 100 coin tosses, number of heads and 1,000 coin tosses, those things do follow the normal curve, right? So we looked at some pictures of that. I told you there's a theorem, the central limit theorem. I don't care if you know what it's called, but there is a theorem. And it basically says that as the number of draws gets larger, the probability histogram for the sum of draws follows the normal curve. As we move along, it's also true that the probability histogram for the sample percent follows the normal curve. Probability histogram for the sample average follows the normal curve, as long as the number of draws from the box is pretty large. Does that distinction make sense? So it's not important that the data itself follows the normal curve. It's not important that the contents of the box follow the normal curve. In fact, in this example, they don't. But this is sort of like, 748 coin flips where it's a biased coin. It doesn't have 50% chance of landing heads, but it's sort of like 748 coin flips. And if you flip a coin or a biased coin 748 times and count the percentage, count either the number of heads or the percentage of heads, you'll have a probability histogram that will look pretty close to the normal curve. Okay? It's a pretty large number of draws. So. Good. Any other questions? Thoughts? Okay. There's that. Let's see. Yeah, so I'll say what else they say about the kind of Chapter 19 issues, which is pretty brief. They also say there are other potential sources of error in surveys besides sampling error. So sampling error is what we call chance error. It's stuff that has to do with random stuff. It's error that has to do with random stuff. So they're saying there are other potential sources of error. However, the overall design and execution of the survey sought to minimize these other sources of error. Okay, so they're not saying very much specific in here, but essentially what they're saying is they tried to design this to minimize bias, what we would think of as bias, systematic error. Selection bias based on how the sample was selected, non-response, and response bias. Okay, so as I said before, I think Field Poll and Gallup Poll do a pretty good job. It's random digit dialing, so it's not perfect. They're not getting people without phones. If people have multiple phones or share a phone, there's some issues there. That's part of selection bias. The non-response bias, not everyone's going to respond, but they do call back 8 times to every phone number. So hopefully, they bother you enough. At some point, you're willing to talk to them, or you're home, or whatever. And response bias, the wording of their question is quite neutral, and they randomize the order of the candidates. So all that stuff is attempts to minimize bias. And as I mentioned sort of near the start of the lecture, other than Chapter 19, we're mostly assuming that the bias is negligible. So mostly we're just assuming that any errors in our estimation are due to chance error, at least mostly due to chance error. Okay? So any other questions, thoughts? Okay, so that's that one. And maybe that's a pretty good time for a break. So let's take a little break, and then I'll get on to essentially chapter 23. Yeah. Okay, so hi. I have a couple of things to announce. One is that Tuesday's lecture was not videotaped, but it was podcast. So if you want, you can listen to it, but you can't see it. And that's my fault. I didn't notify the webcast people that I was coming back with enough warning. So, so it is, like I said, it was audio taped. And actually that, for any of the lectures, this lecture probably makes the least difference because it was all, there's no math in the lecture. So mostly what I wrote on the board anyway was just what I was saying, okay? So if you feel like listening to it, if you missed it, that shouldn't, I hope, be too much of a, makes too much of a difference that it wasn't videotaped. And so I'm sorry, apparently the homework due Monday was not posted. I thought I posted it. There is homework due Monday. I'll definitely do it right now, right after lecture. It'll be on chapters 20 and 21, and sorry, I thought it was posted. And I guess I also owe you an apology about the previous homework that there was never an email announcement sent out for it, for the one that was due this last Monday. So you do have a quiz due on Monday. You do have homework due on Monday, okay? So that's that, okay? Any questions, anything else? Okay. So let's see, where am I? Okay, so that's roughly the end of chapter 21. I want to say a couple more things in closing about chapter 21 that actually also apply to chapter 23. Let's see, where am I? So these are basically, where is it? Basically rules about when confidence intervals work. Okay. So I'll say this. To make a confidence interval, you need normal approximation, or normal curve, I'll say, to make sense. You need normal curve to make sense. So check one, at least 25 draws. So these are the same conditions that I said in chapter 18, that you should have at least 25 draws, and check statistic plus or minus 2 SEs. So the way that I wrote the check before, so that should be, I'll say should be okay. What I mean by okay is in the range of possible values. So in chapter 18, when I said this, I said at least 25 draws, and then I said if you go expected value plus or minus, expected value plus or minus 2 SEs, that should be within the range of possible values. This is essentially the same check, and it'll sort of feel the same to you, but it's kind of technically different because we don't know the expected value. The point of doing a confidence interval in the first place is that we don't know what's in the box. So we don't know the parameter, we don't know the expected value because that would be calculated based on the box. All we know is the statistic, the estimate of the parameter. So this is a slightly different check, although like I say, it sort of feels the same. We're taking that statistic, the thing we know, and going 2 standard errors either way. If that kind of wanders outside the range of possible values, then it's an indication that the probability histogram for the statistic, for the sample value, doesn't follow the normal curve, okay, just like before. And I wanted to mention, I made a little mistake here. When I wrote this up here, the first time I wrote 4.3 plus or minus 3.6. It's 43 plus or minus 3.6. So if you want to go back to your notes and get rid of that, the dot that was there, okay? This is right, 43% plus or minus 2 SEs, 43 plus or minus 3.6. Okay? So if this were like 43 plus, 43 plus or minus 60, that would be obviously very inaccurate, but also wrong, because it would be an indication that it doesn't follow the normal curve. Maybe a better example is if it were just 3. If you made a confidence interval and it ended up being 3 plus or minus 3.6%, that goes negative, right? 3 minus 3.6 would be negative, so that's an indication that there's something wrong. Okay, so the usual confidence interval that you'll do is a 95% confidence interval that is plus or minus 2 SEs. So for a lot of cases, you're automatically doing that check. If your confidence interval includes negative percents or something, you know something's wrong. However, this check should be done no matter what confidence interval you do. So for example, if I did a 68% confidence interval, plus or minus 1 SE, it might be that that interval is fine, it's between 0 and 100, but if I went 2 SEs, it would be outside the range. So in that case, even though the interval I'm making, the 68% confidence interval is between 0 and 100, the 68% and the 1 SE is wrong because it doesn't follow the normal curve. Okay? So this is the check you should look at regardless of what confidence interval you're thinking about. Like I say, even if it's a 68% confidence interval and you're only going 1 SE either way to make your confidence interval, this check is to see whether or not the normal curve makes sense. And if the normal curve doesn't make sense, you shouldn't expect 68% of the area to be within 1 SE anyway. Okay? So the whole calculation doesn't really make sense. Okay, so any questions about this part? So you want to sort of check to make sure the normal curve makes sense. Kind of a chapter 19 issue. You want no bias. And I'll just say, or at least negligible. Okay, negligible. So you want to at least have some reason to believe that things aren't going to be very biased. Okay, part of that is that you should have a simple random sample or draws with replacement. Okay, so technically, having a simple random sample or draws with replacement guarantees that you have no selection bias. So no selection bias. So at least you'd like to have that. So for random digit dialing, I'll often, like that's what was going on here. I'll often say things like, well, you can assume that it's like a simple random sample. Okay, so it's a little bit of an idealization. At least the field poll is not too bad. Random digit dialing is a probability method. It's not quite a simple random sample, but it's pretty good. Okay, so technically, to eliminate selection bias, you ought to have a simple random sample or draws without simple random sample or draws with replacement. Remember, simple random sample is without. That's fine. Or draws with replacement. You still want to think a little bit about non-response and response bias. So non-response, you ought to be reassured that at least everyone or nearly everyone responded. If it's not mentioned, like an exam question, you can figure that you got responses from everyone. So this is sort of, it's not addressed here. The field poll didn't address it. They just say, we talked to 748 likely voters. They don't tell you how many people they called that didn't talk to them. Okay? So it'd probably be nice if they did that, right? It'd probably be nice if they gave us some idea of, well, how many people didn't respond. And then we can sort of make up our own minds whether or not we think the non-response bias is a problem. Okay? But yes, there's non-response bias and also response bias. You might think a little bit about the question wording and whether or not that might affect things. Okay? So to really, kind of by the book, to make a confidence interval, you should have no bias. So you're just dealing with chance error. Okay? Any questions about that part? Yeah. Yeah, so he said if you draw with replacement and you ask the same person twice, is that going to make it biased, or is that just part of chance error? That's just part of chance error. Okay, so that's covered by our standard error calculation. There's one way to think about that is there's no particular systematic reason why any one person should be more likely to be asked twice than anyone else. So there's no kind of systematic way in which that's going to change our results. Okay, so I'm going to erase this. Couple things, couple announcements that were made before class. You should fill out your census forms, whatever. It's good. It's important to be counted. Census2010.berkeley.edu. And ASUC elections, I guess, end today or tomorrow? Today? So today's your last day to vote. OK. Alrighty, so. Oh, yeah, so one more thing I wanted to mention about kind of following along from simple random sample. If it is a simple random sample, meaning a sample without replacement, you should think about whether or not the correction factor should be used. Right? So the thing I did at the beginning of class today, if it's without replacement and the sample size is at least 10% of the population size, then you should also use the correction factor. OK? All right, so that's that. And then next thing. And I'll talk more about this in a minute. Confidence intervals are for parameters. And chance and probability, those words are for, or is for random things. So sample values, meaning statistics, sums of draws, random things. Okay. The parameter is not a random thing. Okay. So I'll talk a little bit more about this one in a minute, but I just want to write this down. It's one of the qualifications for a confidence interval. And lastly, I want to just say that the average and SD are for data, lists of numbers, tickets in a box, things like that. Basically, you can calculate the average and the SD for a kind of concrete list of numbers. You actually have the numbers. You can calculate the average of those numbers, the SD of those numbers. The expected value and the standard error, kind of think of as being similar intuitively in that they measure sort of the center and the spread, but those are used for, again, sort of random things, sums of draws, sample values. So you can be sample averages, sample percents. And we sort of generally think of them as being random things. Okay, but for now, basically, we know how to calculate expected value and standard error for sums of draws, the percentage of ones in the draws, or the average of the draws. Okay, so those are the things that we're using average and using EV and SE for. Okay, questions about any of those bits? Okay, so let me talk a little bit more about 3. That's the one I haven't really addressed yet. So I calculated this confidence interval here for a parameter. The parameter, again, is the percentage of all California likely voters who support Boxer. And I want to kind of I'm going to write down a couple sentences about how to interpret that. One of them is wrong, one of them is right. So it's wrong to say there is a 95% chance that the percent of California likely voters who support Boxer is between it's 43 minus that, so 39.4, and 46.6. Okay? Quote. So that's wrong to say. Now let's think about that sentence. The percentage of California likely voters who support Boxer. That thing I just underlined, that's the parameter. So what this statement is saying is that there's a 95% chance that the parameter is in that interval. Well, when we say chance, what do we mean? When you flip a coin and you say there's a 50% chance it lands heads, what you're saying really, technically, is if you flip that coin over and over again, in the long run, you expect it to land heads about 50% of the time. Okay, so that's what we really mean when we talk about chance, is you want to think about somehow this procedure that we could repeat over and over again. Well, there's nothing like that going on in this sentence. There's a parameter, the percentage of California likely voters who support Boxer. That's some number. I don't know what it is, but it's some number. It might be between these two numbers. It might not be between those two numbers. I don't know. But it's not sometimes between those two numbers. The way, like, if you toss a coin, sometimes it lands heads, sometimes it lands tails. This is some fixed percentage. The percentage of all California likely voters who support Boxer is, if you just asked everyone, all the likely voters in the whole state, if you actually managed to talk to all of them, you'd get some percentage. And like I say, it would either be in between those two numbers or it wouldn't be in between those two numbers. It's not sometimes in between those two numbers. Okay? So the right thing to say is to address this in terms of a confidence interval and to say we or I am, we are 95% confident that the percentage of California locally likely voters who support Boxer, the percent of California likely voters is between 39.4 and 46.6. Okay? So that's fine. So essentially the difference is these words, 95% chance, 95% confident. So chance has a particular meaning to statisticians and probabilists and people that care about these things. And like I say, it means that you are talking about something that you could repeat over and over again, like tossing a coin, rolling a die, something like that. And sometimes you get one result, sometimes you get another result, whatever. Okay? Random things are happening. So since a parameter is not like that, it actually is some number. It's unknown, we don't know what it is, but there actually is a number there that could be between these two numbers, it might not. We don't like to talk about chance with that situation. So this confident word is sort of invented by statisticians to deal with the situation where it sort of feels like chance, but it's not quite chance. You may think of it as sort of pseudo chance or something like that. It's not random because this thing, the parameter, is not a random number. It's not sometimes in there, sometimes not in there. So you kind of think about this as being, I don't know, roughly in some ways similar to chance, but it's not actually chance the way we define it. Okay. One way I like to sort of make this distinction is to think about chapters 17, 18, and 20. So chapters 17, 18, and 20 are like throwing a dart at a target, which is the expected value. Okay? So we're doing something random, like taking the sum of draws. In chapter 20, we're taking percents. And also true in the beginning of chapter 23, we're talking about taking a sample average. So that sample value, whatever it is, sum of draws, sample percent, sample average, should be close to the expected value, but it might be off by a little bit. The amount off, the chance error, is measured by the standard error. Okay, so the idea behind this is that there's a random thing. That sample value is random. It's going to be close to the expected value, but it might be off by a little bit. So chapter 19 and 21 and the end of chapter 23 when we talk about confidence intervals. When we talk about confidence intervals, I think of this as being like, what's going on in these chapters are like throwing a ring which may or may not cover an invisible stick. Okay? And the invisible stick is the parameter. The ring is the confidence interval. So the book has this picture which sort of mimics this idea, which is that the confidence interval is based on a sample. So if you took a different sample, you get a different ring. So every time you take a confidence interval, it's like throwing a ring, and you're trying to like throw it over a stick. The problem is you don't get to see where the stick is. So you don't know if you actually managed to cover it or not. All you know is you know from the rules of probability that we've done in other chapters that our process of throwing the ring is pretty accurate, right? We ought to get pretty close. The statistics should be pretty close to the parameter. We have an idea from the standard error about how far off we might be. So we're pretty sure that this process of tossing this confidence interval, this ring, we're pretty sure that most of the time we should manage to cover the stick. We don't know for any particular confidence interval whether or not we've succeeded, but at least the procedure makes sense. So if you think about this idea, now again, this picture is a little bit of a lie because in reality we don't get to see the stick. But there's a picture in this book that does this, basically, okay? These are confidence intervals. So these confidence intervals, like I say, the confidence intervals themselves are random. If we take different confidence intervals, some of them will cover the parameter, some of them will not. Just like if we toss a coin, some of them will land heads, some of them will not, right? So there is randomness in the procedure of making the confidence intervals, but once I've made my confidence interval, once I've made this confidence interval, either it includes the parameter or it doesn't. This interval either includes the parameter or it doesn't. It doesn't. This interval does not sometimes include the parameter. So that's the distinction I want to make here, is that if we make many confidence intervals, there's randomness in the confidence intervals, so some of them will cover the interval and some of them won't. But once I get one, and typically all I do is I get one, right? If you actually do this in real life, that confidence interval that you got either covers it or not, okay? So that part is not random. That's basically the distinction I want to make. Okay? So this one missed, most of them hit, whatever. Okay? So questions? Okay. So Tuesday I'll basically do the last part of 23. I've done basically the end of 21. There's a little bit of 23 having to do with confidence intervals I want to finish up with. And then maybe the second half of the lecture, I'll start chapter 26 Tuesday. Okay, have a good weekend.